With us Dr. Robert Hawks from Nelson University, who's, as I can tell from the discussions that have been going on, known to some of you for sure, well-known astronomer, and he, with a number of colleagues, right now is anticipating a maximum rather, in the Leonid meteor shower, probably next year or 99. And there is more than a finite danger, they have been saying for some time, to spacecraft, satellites, etc. And Bob is going to talk to us about that. So my name is Richard Hurd. I'm the chair of the Public Awareness Committee for Meteorite Impacts Advisory Committee. And we do have some information about the committee at the door. There's an abstract of the talk tonight, if you'd like that. Some of you have already picked it up. So I think without further ado, I will let Bob talk to us. Thank you very much.
Okay, well, it's really great to be here in this beautiful facility at NRC, and I'd like to thank the Canadian Space Agency for arranging it for the session tonight. Just before I start, I just want to relay, I think it was a little less than 2 decades ago when I was at the first international conference that I'd been to as then a recent grad student in meteors. And I guess those of you that have been through the similar experience, it's all these people that until that point you've just seen their names on papers and you kind of elevate to godlike status, and then to meet them all you say, wow, that is so-and-so, and that is so-and-so. So this was a big experience, but I clearly remember at that conference, at one point I was sitting around with some of these people who I understood then were real people, and they were discussing where in the world was the place to be if you were studying meteors. And I was more than a little proud when quite a few people said that Canada was the place to be. And the reason I'm starting with this story is in many ways Canada is the place to be because of the contributions of Dr. Ian Holliday, who's here tonight and has been very active in MIAC, and we're going to be honoring him actually tomorrow. And his colleagues, the late Dr. Peter Millman and Bruce McIntosh, who through so many ways, over so many years, through the Meteorite Observation Recovery Program, through involvement in a host of international conferences, through the International Astronomical Union, through a huge number of top-rate publications, really made an amazing contribution to the field. And I'm glad that some of that work, well, I guess no longer continuing right here at NRC, is continuing in Canada, and I'm very much in what I'm going to talk about tonight, to talk about that contribution. But I did want to acknowledge, since we are in NRC here, the outstanding contributions that Ian has made to this field. And I will have a few meteor spectra in the presentation. This is more or less what I plan to talk about. I'm going to give you a little bit of history about the Leonids and their parent comet. Give you what most of you are perhaps most interested in. What are the predictions? When is it going to be best? How good is it going to be? When should I observe? What part of the Earth do I need to be in? Talk about hazards to space operations. And I should say at the outset that is still not well understood. I think the hazard could be quite significant, or it could be totally negligible, and no one knows that firmly yet. Hopefully after this year's observations we'll be able to pin it down a little bit. Then I'm going to talk about observational plans both in this coming fall, that's coming quickly in a few weeks' time, and then also the tentative plans for the following year. Now, I had expected that this might be a little more general audience than it actually is, and so I was going to say something very general about comets, but you should always start any good presentation with a few pretty pictures, so I think I'll do that anyway. All right. Meteors, at least most meteors, as opposed to meteorites, come from comets. This is a picture of of Comet Halley, another famous comet west that probably was the last comet to rival the sort of spectacle we had with Hale-Bopp and then Hyakutake in the last couple of years. And when those comets come near the sun, the dirty snowball of the comet begins to evaporate and dust grains are released, and those become the meteors. Because of mainly the radiation pressure from the sun, to some degree the solar wind, that material is blown almost straight away from the sun into two tails, the ion tail and the dust tail. The meteors we see in meteor showers are not that material, which is rapidly lost from the solar system, but larger material that remains more or less, still somewhat radiation affected, but more or less in the orbit of the original comet. This is an artist's conception of what one of the earlier Leonid storms might have looked like. And you can see here the perspective effect you really have that the meteors are in parallel orbits, but in the same way that railway tracks on the prairies appear to radiate from a point, so will the meteors appear to radiate. That's sort of an artist's conception. The following, not for the Leonids, but for the Perseids, a photograph done by some Japanese amateurs, shows this effect very well. You can, those of you that are astronomers will recognize Perseus in the top left there. This is the Pleiades down here near the bottom, and you can see the various trails. If you extended them back, the radiant would be in the top left of your picture. And that's what we get for each shower. I think at this point now, I'll be it for slides for a few minutes. But a picture is worth 1,000 words. This is one of the famous pictures that I've seen over and over again in Sky and Telescope and other magazines the last little while. And you'll see lots more, I'm sure, in the next year and a half, taken during the 1966 Leonids. And in 1966, it's estimated that there was perhaps as many as 150,000 visual meteors visible in a period of about an hour or slightly less. Truly spectacular. Let's look at what we could figure out about those meteors from this single picture to give us some idea of what we should be aiming for this year with observations. Okay, the first thing that you could figure out is the radiant, or point they seem to radiate from, because this picture is fortunate enough that there are two almost head-on meteors right there that define the radiant really well within the sickle here of Leo. You can also notice here, you could figure out something about the relative numbers of bright and faint meteors, that is large and small ones, and we'll see that's one of the most important things for evaluating the hazard due to spacecraft. I would argue you can also say a little bit of something about the physical structure. If you had one of these little Leonids, and most of them are small, the things that make the meteors here in this picture would all be much smaller than a pea, probably. If they were a solid, hard object, you can show from physics that you would expect their brightness to gradually increase as they're getting lower in the atmosphere and its greater density, and then to tail off rapidly at the end. There are a few of them that to some degree seem to do that. Let's find one that does it pretty well. That one's not too bad right there. It's hard to see some of these up here. These ones are about the middle and so on. But remember, all these meteors are going from the center out. But what you'll see is that a number of these aren't following that pattern, but actually get their brightest point quite near the beginning and then tail off for quite a while, and that there is no one pattern. What that probably is indicating to us is that they're fragmenting in flight and that they're actually a fairly loose sort of material, and that may be important in terms of the hazard that they pose to spacecraft. Well, that's our picture. Let's move on a little bit to the history of the Leonids. The first recorded shower in kind of recent history that's well authenticated was in 1799. Meteor shower rates are specified by something called a zenithal hourly rate. That's the number you could see if the radiant was directly over your head and you were somewhere the darkest possible skies, you had good vision, could see 6.5 magnitude stars, the number you would see in an hour. So around 30,000. There was a good return in 1832 and 33, somewhere around 10,000 actually observed, but that would correspond to a ZHR because of where the radiant was and other effects of around 100,000. 1866 to 67, or somewhere around 5,000 observed. The parent comet for this, Tempel-Tuttle, was in a sense discovered in 1865. It was later found in an earlier passage to be the same comet, and was recognized 2 years later as the parent for this shower. It has a period a little bit over 33 years, and that's why the Leonids are strong every 33 years, or at least some of those periods. There were predictions that 1899 would be good, and then a few people predicted it wouldn't because they saw that Jupiter was perturbing the particles, and then in 1899 there weren't any, and it was the comet Hutek factor, and people said, oh, they predicted, those astronomer types, they predict something spectacular, and it wasn't again. Now, what a lot of people miss is that actually in 1901, 02, 03, there were pretty good Leonid rates. So it wasn't that there weren't any good storms, they just were a little bit later. There were rates of near 1,000 an hour in those years. 1930, 31, 32 weren't very good, around 250. So not too many people were watching when on the West Coast or the Midwest in 1966, there were more than 100,000 meteors seen. Different people define meteor storms, which is what we're talking about here, in different ways. Generally, it's something with more than 1,000 visual meteors, and these would be the years that there were storm conditions. Now, if you go back to ancient records, which people have done, Korean, Japanese, Chinese, and other records, you find that there were, in fact, some of these, I'm not sure how well I believe, the references are pretty brief, but there were 58 Leonid events since 902, and certainly in 902 there was a truly spectacular Leonid storm. Well, what about this comet? There's amazingly little known about this comet. It's truly surprising. Here you have the most spectacular, without doubt, meteor storm produced by comet Tempel-Tuttle. When was that comet observed? Briefly in 1366, on a single night in 1699, a bunch of times in 1865-66, and then recently, it wasn't detected in 1899, wasn't seen in 1932. It was recovered by Karen Meach and people she worked with using the Keck 10 meter on March 4th, 1997, when it was about 22.5 magnitude with no coma. The coma, that was valuable because that allowed us to estimate the size, and most people feel that it's 2 kilometers within a factor of perhaps 2 for the radius. It'll be in perihelion on February 28th, 1998, and it will be, if you're a comet observer rather than a meteor observer, your best time is probably early in 1998, and it'll reach about 9.5 magnitude. Now, Don Yeomans, who studied this comet extensively, pointed out at a conference I was at a couple months ago, this remarkable fact, that in new moon conditions on October 12th, in the year 901, this comet was within 0.008 AU of Earth, and yet there is no record that anyone has found of this comet. It should have been spectacular. And that's amazing. Because you might say, well, that's a long time ago. Records maybe weren't good back then. But for example, Halley can be traced back more than 2,000 years. So why is this comet so unspectacular and its meteor so spectacular? I'm going to actually end the very last slide I have is some speculations on it. Well, that kind of wraps up history. Let's move on to stage 2 of the 5 stages in this presentation, and that is, when is it going to be best? Well, there's various ways you can predict it. There are at least 6 sets of predictions out there, none of them done by me personally. Don Yeoman says, well, the simplest approach is simply look at when the comet goes through the orbital plane of the planet, look at when the Earth is nearest to that point where it went through, and that's your prediction. And it turns out that's not as simple as it is. That's almost as good as doing anything. And that would predict that in 1996 rather, this year, last year, that would be November 17th at 7:20. That was right within at least a few hours, it would seem. And that this is just the number of days that, between when the Earth was at that point and when the comet was at that point. Well, what about this year? Time to watch, November 17th, 1334 Universal Time. You might say, well, gee, isn't this the best year? And in fact, there is at least one person, Brian Marsden, who thinks it might be. But most people say, no, you've got to watch, the next overhead will explain this a little better. It's not just when you're closest, but it depends whether you're coming before or after the comet. So almost everyone's saying 98 is the best year, except for a few people that say 99. And on 98, it'll be November 17th at 1943 Universal Time, and 99 it will be here. Now, my colleagues at Western have done a bunch of modeling here where basically what they do, they put in reasonable assumptions for the size of the comet, how it ejects the meteorites, they trace thousands of these particles around to see when the Earth intersects most of them. When you do all that, your predictions aren't much different from the thing you do in 5 minutes, really. They're a little bit different. So it's 11 Universal Time versus 1334. The main difference is they can predict with more accuracy how many meteors that you would have. Now, this is important. This says where you should be to watch it because you need to be in darkness at this time. So ideally, you would want the radiant high in the sky just before dawn, and you want to be somewhere that it's dark then. Western North America or out in the near Pacific would be the place to be this year. This is not good news if you're Canadians, I'm afraid, as you've probably seen. Next year, the place to be is Southeast Asia, around Japan should be pretty good, and then a little bit further into mid-Asia in 99. In terms of moon, as probably most people in this room know, this year couldn't be much worse. It's virtually full moon. Next year, though, is almost right on new moon, and it's superb. What are the rates? Well, the predictions are all over the place. These are sort of an average of what different people are predicting, but don't take them as much more accurate than that. 1997, we might see a few hundred, would be my guess. 1998, we'll see somewhere between a few hundred and a few tens of thousands. That is, most people are saying it will not be as good as 1966, but will be better than the real dud years. 1999, surprisingly, the models predict almost as good in 99 as 98. So that finishes the predictions part. Other than, let me clarify this business so it's not just where you are. This looks fairly complex. It's a diagram that Don Yeomans from Jet Propulsion Lab did a number of years ago in a paper. It's been widely referred to since then. Basically, what it does is it divides things into 4 quadrants, looking at whether in a given year we were either ahead of or behind the comet, and we were either in a bigger orbit that is outside it or inside it. So you have 4 possibilities that are given here, and then you plot, and the really spectacular Leonid storms like 66 and 1833 have kind of a star, and the pretty good ones have a big dot, and the not so good ones a smaller ones. Now, the problem is, I mean, to some degree, this looks like it's best when you're behind and outside the comet. This, for example, is where we are in 97, so that isn't true. This is where we are in 98 and 99. But it's also generally better the closer you are kind of down here. But if you actually look at the rates here, some years that were quite good, like 902, is somewhat up there, and other years that were duds are slightly below. So it can't be extended too far, but that's kind of the prediction. That's a simple way of predicting them good in 98. Well, one question to ask is, has the storm begun yet? Well, the storm hasn't begun, but the increase in Leonids, you put together International Meteor Organization data here, plotted against solar longitude. So one there is, one on that axis is roughly a day. You can see here that there's a pretty sharp peak here in the Leonids. This is the 96 data, and in fact, from 94 on, there have been effects of varying degrees like this. The green are not Leonids. They're an average of all the sporadics observed by the same observers to give you some kind of reference. If the sporadics were going way up too, then you'd be looking for some systematic effect. For the most part, the sporadics, it's a control that looks pretty good. The next slide is simply the same thing looked at in more detail. So I've expanded this axis, and you can see it's a pretty sharp profile here. The peak is only about an hour or so, at least the really sharp part of the peak. It's certainly the order of an hour or two, as opposed to showers like the Perseids that are pretty strong over a day or two. Well, what the heck? You probably should actually see a few Leonid meteors rather than listen to me talk about them. So I'm going to turn off this overhead. Now, I was talking to someone before, and they were talking about, wow, so-and-so doesn't make that much actual visual meteors. I can never actually fault anyone on that, because I must admit to you that I almost never go out and freeze or get bitten by mosquitoes and sit there endlessly watching a few meteors go by. My idea, can we have the lights back on for a second, Richard? I got to find this.
That was inadvertent.
Oh, I thought my talk was over or something. My idea of meteors that I learned at Western was the way to watch meteors is you hook up a bunch of intensified TV equipment, you set it in the yard, you put a monitor inside a building somewhere, and you go in there in the warmth, drinking coffee and watching the screen every now and then to make sure your lenses aren't too bad. So anyway, we went out. Now, it wasn't quite this comfortable, actually, for last year's Leonids. We went outside Sackville to a little place called British Settlement and actually set up 3 of our systems with monitors in this car. And we just, Sackville was a small and trusting place. We wanted to find a good observing location, and the student that was working with me, Dave Babcock, simply went along and knocked on these people's door and said, your field would be good. Could we kind of come out here and spend a few nights in your field and plug into your outside plug? And people said yes. And so we went and did that. And we got, here are some Leonids from 96. It's about 20 degrees across the field of view here. Yeah, maybe. It's more like a true astronomy experience. Yeah, let's turn the lights on. Most of the meteors will be on here a couple times. The radiant at this point was above and to the left, and so most of them, but not all, you'll see here are Leonids. The faintest stars you can see here are about 9th magnitude, and this is real time, so we have 30 frames per second of this, which we then digitize using computers and do various analysis, mainly looking at physical structure. Little wee faint one there on the bottom right. Oh, she missed it. Not as easy to see as the others. Right now we're looking at part of Gemini. M35 is just to the right of the black spot on the top left there. It's a little cluster. Just let you know the area of the sky. The kind of foot of Gemini. We've got about 60 meteors over this night on at least our best system. These aren't Leonids, these few. Something I thought would be interesting, the astronomers here, something we set up this summer was we hooked up a 10-inch telescope to an image intensifier in our video CCD detector. So we have about 1 degree field of view. So meteors go by real quickly here. And faintest stars are about 13.4 magnitude. We did this because one thing we're interested in is how the light is distributed with time and looking for little flares that are indicative of fragmentation. We want to get more resolution. This is the same meteor from the same location but with around a 20-degree field of view. Again, the faintest stars here are about 9th magnitude or a few 9.5 magnitude stars. So that was the same meteor that seemed so fast in our small field of view. So what we do is we have a kind of a blown up picture of a little bit of the trail, and we know which little bit of the trail we have. And one of my honors students, Margaret Campbell, is actually working on this for the Perseids and the Leonids, doing a comparative study. This is interesting. One of these is the same one you just saw. These are two meteors, apparently unrelated, almost simultaneously. Hundreds of hours. I haven't seen anything quite like this before. It's pretty neat. And then the last bit of the video here, or at least the last bit we're going to see today, I do have some of the peak skill fireball we'll look at after. This is, we're just beginning to try to learn about doing some spectra here. So we have a 300 lines per millimeter blaze grating in front. So you see spectra of some of the stars. Preferentially puts the spectra on one side. And then you have a meteor in its spectra. While the resolution is just terrible compared to photographic spectra, the advantage is we get quite a few. We get around 6 or 7 spectra an hour. And also that we get time resolved steps along them. See that one again, and then it goes to, I just froze on pause. So you can kind of get some idea that there are, spectral lines structured there and so on. So these are from the Perseids of just this past summer, but we are planning to, in the observational campaign, I'll talk about one of our cameras doing spectra in California. Thank you. Basically, you're interested in putting together an image-intensified TV system so you too can watch meteors without freezing and getting bitten by mosquitoes. There isn't really much to it. It's almost embarrassing how easy it is to make these things. Generally, you use objective lenses that aren't much different from 30mm camera lenses, like a 50mm or something focal length, as fast an f number as you can afford, or steal, or borrow, or whatever. Then you want some kind of image intensifier. Most now are what are called microchannel plate image intensifiers. These things are about the size of my fist. Inside, they have about 20,000 volts that produces. You have a photocathode surface, then you accelerate the electrons and produce basically many photons for each one that you put in. They have an optical gain of something like 20,000. That is, the brightness on the output's 20, 30,000 times as bright as the input. There's just a little output phosphor window, like a tiny screen there. Then you couple it in some way to a CCD detector, but not a conventional astronomy CCD detector where you integrate over 5 minutes or 2 minutes or something like that, but rather one that's run at video rates, that is 30 frames per second. And then the rest of it, you put the time and date on it, VCR, and so on. In terms of cost, to get a fairly good quality one, these things are still the order of a couple $1,000s, the order of $1,000 for a good one, the order of whatever you're going to put into your lens, hundreds of dollars, and so on. On the other hand, if you want a system that's almost as good, and in fact the one you saw hooked up to the telescope was put together with actual surplus parts, we're upgrading it right now, you can buy these things kind of military seconds for about $400, and you can certainly get some kind of cheap monochrome detector for a few hundred. So you can actually, for not much more than $1,000, put together some kind of a workable system. Let me just mention a little bit of what you can do. I alluded to it earlier. And in particular, one of the things that interests us most is to look at the distribution of light with time, because basically the light produced by a meteor is an indication of the instantaneous kinetic energy of the ablated or evaporated material. So if I had a meteor like this that broke into two pieces, it now has more surface area. And in the same way, if you split wood in a fire into kindling, it burns faster. Even though the meteor is not burning in a chemical oxidization sense, it's still true that with more surface area, it evaporates faster, and you would see a bump on the light curve, like you might have here, or that would be an indication. Now, you get truly sharp flares on a few of the photographic ones. Most of the TV ones, it's very subtle. And the honor students working with me on this, we've had to do a lot of kind of curve fitting to try to get data out that's just a little bit above actually the noise. Why are we so interested in physical structure? Well, if the meteors are really clusters of thousands of grains, perhaps released even before they enter the atmosphere, that would mean spacecraft would be impacted by collections of whole bunches of small grains. Depends on the exact surface of the spacecraft, whether that's better or worse, but at least we should know if that is the right physical structure. Let me see. Every physicist has to have at least two equations in a talk, so we'll do them on these two slides. If you want to see how, when we do spacecraft hazard, which is what we're just about to, the critical thing is how many meteors are there of different masses. So, for example, the meteor you just saw there, what was the size of those brighter meteors? Well, the answer is the size was something the order of 10 to the minus 7 kilograms. That's right, 10 to the minus 7, truly tiny objects here. You might say, how is that possible? It's because really of the v squared term, and what makes the Leonid such a big hazard is they're coming in at 71 kilometers per second. So v squared in 1/2 dmv squared is big. So what you do, you basically take the light curve, the shape of light versus time, integrate over it, put in some constants, there's a v squared term here, and you get what's called a photometric mass coming up. Now, should you believe me when I said that was 10 to the minus 7 kilograms? Probably not, because it's dependent on what this luminous efficiency factor is. Most people make a simple assumption that it's roughly proportional to velocity. The problem is no one has calibrated this for meteoroid-sized objects anywhere near 71 kilometers per second. It's like a huge extrapolation. And I think most people would agree that we don't know masses, photometric masses, better than a factor of 10 for the Leonids. So when I tell you one's 10 to the minus 6, it might really be 10 to the minus 5. Let's keep that. Okay, this is second. Oh, and the third equation here, all in one. You usually represent the number of big and small meteors, which is important in evaluating the hazard by something like this. The number between mass m and m plus dm turns out to be proportional to this, m to the minus s, or if you integrate it, which is what you really measure, the cumulative number bigger than mass m will be given by this. This s is really what determines whether you have lots of faint ones, if s is like big, like a number like 2.4, or if you have relatively only bright ones, like in the Perseids, where s is a number like maybe 1.7. And that s is called the mass distribution index. So ideally, what we really want to know most, and what we're trying to get out of this year's campaign that I'm about to go into describing, is what is the flux, what is the number per time coming in, what is the distribution in sizes, how many are there of different masses, and what is the physical structure. Are they one compact object, are they clusters of grains, or something in between? Now, just before I leave this, is an important point here. I alluded earlier, there was relatively little evidence gathered in 1966. The most valuable evidence was actually from two places, here in Ottawa and in Czechoslovakia, and those measurements did indicate that during the peak of the Leonids, which Data has just been reanalyzed and republished in the last year. During the peak of the Leonids, which lasted less than an hour, there is evidence that the mass distribution index was high, 2.4, 2.5, which means they were really rich in small particles. That means the hazard is relatively great, because we know how many bright ones are. The question is, are they really tailing off or not? So if you now, one of the things we did with our data, and we're about to send off to a journal, the data we collected from the cars in British settlement, from the people that let us just drive up and use their land, we did a plot of log cumulative number versus log mass. This would be a straight line if the function I just showed you on the equations was right. Its slope gives you S. From that, we were down to about a 9th magnitude limit meteors. We get S of 2.22 with a fairly big uncertainty because our data size is small. That's higher than some other people got. That tends to tell us that we were getting still lots of meteors, quite faint, and that might indicate we're closer to maximum than some people think. Or at least that's something we speculate on in the paper. Well, what about the hazard to spacecraft? Let's move on to that second last part of this talk. There are two, I'm going to do this in a fairly qualitative fashion, but I'll be pleased to answer to some degree more quantitative questions if people have them after. There are really two dangers. One is a direct impact hazard, where you simply have something go right through some critical surface on your space vehicle. The other that wasn't realized so clearly to the last few years is a plasma electrostatic discharge effect, where a spacecraft has different parts of it that gradually in space get charged to different amounts. And when a tiny meteor, so now we're talking about something that could be smaller than this, impacts that, then what you have is a little plasma created, which creates an electrical path for discharging quickly one part of the spacecraft to another part, which can interfere seriously with electronics on the spacecraft and perhaps even render it unusable. It is controversial, and I know that the official version is that Olympus, a communication satellite valued at $800,000, that was wiped out within 2 hours of the 1993 Perseid maximum. The official report is of unknown causes, but many people feel that it was actually struck by a meteoroid and perhaps an electrostatic discharge effect. Well, let's look at a little bit here about the impact hazard, which is the easier one to evaluate. The International Space Station is being designed so it can withstand a 1 centimeter diameter aluminum sphere traveling at 10 kilometers per second. You might say, why do they do 10? Because the slowest natural meteors are 11.2. It's because they perceive the main danger to be space debris, stuff we humans have put up there in rather than natural meteors. Now, Leonids have much higher geocentric speeds. If you assume that the damage is proportional to kinetic energy, and that's not necessarily true, then this would correspond to a Leonid of mass 28 million grams, 28 thousandths of a gram, or something like a 0 magnitude Leonid. So that means that you'd have to have one a bit bigger than any you saw here on TV to directly impact the International Space Station. But most other space vehicles are less protected by factors of 10 to 100, so you get down to there's clearly a danger at about 5th magnitude. Or in other words, just to put it in perspective, we saw 60 meteors from that location last year, well before this the really enhanced storm that we're going to have in the next few years. Any one of those could have wiped out an $800 million satellite. But the probability of that happening, if you actually work out a flux, and there's numbers here, and I was going to, Peter Brown at Western and Martin Beach at Campion College in Saskatchewan, and Jim Jones also at Western have published a bunch of good papers on this, looking at it different ways, evaluating what the hazard is. Went through a bunch of those, but I said coming up in the plane, they just do something really simple. I have my calculator with me, And so what I did was I took the number of meteors we saw, and I said, let's assume the mass distribution is the same as the sporadics, because that's probably about as good a guess as any. And I'd say, let's say that in the storm, instead of there being 10 Leonids an hour, there's going to be 100,000 Leonids, kind of a worst case scenario. And I took the observing area that we had, number of square kilometers, and number of meteors we had. I multiplied that by 100,000. And then I said, well, how many space vehicles are? I believe, and perhaps someone in the room can correct me, that there are about 700 useful space vehicles up there. Their effective surface areas, their targets for Leonid meteors, vary all over the place, from being somewhere on the order of, I think Mir is about 500 square meters, a pretty big target. Many are around 100. The International Space Station will be about 1,000. So I said, well, most of them are small. Let's say 100 square meters on average. So I took my 700, I multiplied by that, and you can figure out what would be the probability of one of them. And I assumed that like fifth magnitude was kind of what would wipe one out. And you get that the odds are that there is about 7% chance that one would get hit, which is fairly high. But remember, that's a really worst case scenario of 100,000 visual meteors and assuming this rather high S. The amazing thing is, if you kind of go through it really carefully and you look up the papers, you get numbers that are that order of magnitude, a little bit less than that actually. Now 7% of one of, that doesn't seem very much, but remember, if it's worth 800 million, 7% of $800 million is a lot of money. Now, we would be happy to have that 7% of $800 million to study this for them. But in honesty, we should say, what can we really do that's of much use? And in a way, we can't do much. I mean, it's like we can perhaps predict what the chance is that your house is burning down right now. But what real good does that do? Not much. For the Leonids, there are a few obvious things that you can do without a prediction. That is, you could, the solar panels on spacecraft are the biggest target. You could orient those so that they're flat to the radiant. Space vehicles that you are able to control their orbits then you could put them on the backside of the Earth, because remember the Leonid maximum is only going to be about an hour when it's a high, severe thing. You can close the flap on the Hubble Space Telescope. Most of those things were done for the 93 Perseids. You can delay shuttle missions. You can do all that without a prediction. I guess the main thing a prediction would give you is just, is it worth, because there are some costs to doing all those things, is the danger big enough that it's worth doing it? And we have interested in some funders, and so various organizations are funding us to look at that. So I think I will move on to what, first of all, the plans for this year. And it's scary to think that this is only a few weeks away, since we still have lots to do. This is the plan. It's now pretty firm. We are going to have what is arguably the world's best radar committed to meteor work. The radar is valued at several $1 million. It's costing $100,000 to rent it for 1 month. It's produced by Raytheon, normally used to detect actually ballistic missiles and Scuds and stuff. So if anyone attacks California, we'll be the first to know. But it's being modified as a meteor radar. Now, I don't know much about the radar. I'm involved in the TV end, as you probably gathered. But the one powerful feature of the radar is all the data is digitally collected and all the beam forming is done after the fact. So you can kind of decide what you want it to do after the fact, which is nice. The other thing is it's frequency agile, in that we will have antenna fields set up. We need about 10 acres for the antenna fields set up so that it can run at 20 megahertz and it can also run at 30. And there are advantages in doing that. It will basically be sending out radar pulses in fairly omnidirectional fashion. But note that the only ones which will get reflected back are ones that meet what's called specular reflection. That is, that there's perpendicular. So these are your Leonid meteors, all in parallel orbits, occur in various places. None of these ones, though, will produce an echo. The echo will be right here. Why am I stressing this point? Well, it has importance for the TV part. The radiant, or where the meteor is seen to radiate, is here. As the night, that will start off low, will be rising a bit before midnight, will get higher in the sky just before dawn. Meanwhile, the echo line, the place you could see meteors, will be going further and further away and setting with that. What the main plan is we're going to have several TV cameras looking along this echo line so that we will have the same meteors that will have their electron cloud from the radar, their range from the radar, their line in space from the TV, their entire ablation profile from the TV, and their fluxes from both. So, and we're going to be doing this, I don't think I mentioned this, originally we were trying to go to New Mexico, but for various practical reasons, we're now going to be at Edwards Air Force Base in California, where the people have been very kind in making arrangements for us. Some of you amateur astronomers will appreciate this. We said, well, we need these 2 sites for the electro-optical. And we said, now we don't want vehicle lights to give us trouble with that. And the person at Edwards said, don't worry, we were planning to set up submachine gun posts. There will be no vehicles bother you. So if you just want night conditions, you know, just get some military people to set up machine gun posts. They also later said, oh, by the way, because we're going to be up 12 hours every night kind of following these things through the echo line, which is going to be somewhat demanding. 4 of us are working on this. They also said that they're going to have military people all the time to make sure we don't steal secrets in the middle of the night. But anyway, so that's what we're going to be doing. Now we're also, just to make this even more challenging, when I originally committed to this is what I thought we were doing. But then they said, no, we want 2 station also. That is, if you observe the same meteor from 2 TV stations, you can triangulate and get its radiant really accurately. So we're going to have 3 other cameras, also on Edwards Air Force Base, about 80, 90 kilometers along. So we're going to be about 40 or 50 kilometers, but still on Edwards in another station that will have worked out the geometry and be following the same meteor line through the space and trying to detect the same meteors from there. We also will be using a couple cameras, one to stare into the radiant, which I think is what the best thing to do for a variety of reasons. Those meteors are coming almost head on. We'll be able to detect fainter ones, which I think is important, and we'll use one for spectrum. We're going to have in total, we're constructing them right now. We've got funding for, we're building 8 new image-intensified video systems, along with the 3 we currently have. We'll have 11. One of those is to go to NASA in Houston. They're running it with their radar. Another one will be running in Western, and the rest of them will be running in California. Partly thanks to some travel funding from the Meteorite and Impacts Advisory Committee, which we are most grateful to help this project go along. Those are the main goals. These are some of the people involved, and it's being coordinated through ISTS, the Institute for Space and Terrestrial Science, which have now been renamed CRESTEC. I'll just put this on briefly before I talk about plans for the next year. My colleagues at Western, they're running all the radar stuff, put together what a similar radar would have detected, this is what the pattern was, if it was running in 1966 when they were so spectacular. And this is range plotted up here, and this is time in minutes, and every bit here is an actual echo, right? And you might say, that's wonderful, you're getting so many meteors, that's like more meteors than I'll ever see in my life in 14 minutes. Well, it's too much of a good thing, because when you have meteors on top of meteors, you can't actually interpret them so well. So they're doing clever things that will actually separate out, give us fewer meteors, but clearer data through data analysis. Well, what about 98? Because although we're building all these cameras and we're going to California, the moon, remember, is almost full, and the cameras will not be nearly as good as they could be. In 98, we are part of a program which is being headed up by Peter Jeniskins from NASA Ames, along with someone from the U.S. Air Force. And there are about 12 other collaborators, mainly from Canada, Czechoslovakia, the U.S., and one from the Netherlands, I guess. By the way, for this project, the Leonid Meteor Outburst airborne mission, there is a web page here, if anyone wants. It's full of excellent information on the Leonid, set up by Peter Jeniskins at NASA Ames. and the airborne itself is described here. Let me go through what the plan is. Well, these are the, I believe, the webpage part of. These are the people that are involved. Now, at this point, this is a proposal. It's at the NASA Planetary Atmospheres and Planetary Science or something else. The project requires a lot of money because basically, as I'm going to mention in a moment on an overhead, the project involves flying 2 aircraft in Thailand and doing observations from the 2. And flying aircraft, I didn't realize this, with scientific windows is ridiculously expensive. So the program is seeking about $1.3 million, and virtually all of that is just for travel in the aircraft. That is, they're not providing any money, say, for us for operating our own equipment. We have to worry about that. Anyway, these are the various people, and I'll talk a little bit about the experiments. And we hope to know whether this is funded by NASA within probably a month or 2. The plan is to fly 2 probably NASA aircraft at about, well, I'm trying to get them to make this last, but the current plan is at 250 kilometers separation. And they're going to be flying at a height of about 10 kilometers. And what they'll be doing is they'll actually be doing triangulation from the 2 aircraft. And you say, well, won't that be terrible? The aircraft will be rocking a little bit and so on. It turns out that it's not as bad as you think, and they actually did a task with our people that are so helpful at Edwards Air Force Base in California this year's Perseus. And on TV, the stuff looks quite good and stable. Now, on the longer exposures, since they're also doing photographic work, you do get, like, your stars are like this and so on. And what they're doing is, once they see a meteor, they're going to end their exposure, and they're going to count on the fact that they'll know which of the jagged ends is the end. It sounds a little hairy to me, but that's, anyway, we're in the TV side. And on the TV side, where it's only a 30th of a second from one image to the next, I don't think there's going to be any problem. So you have a bunch of optical windows in the aircraft here. There will be TV, ordinary TV, very high resolution TV like the ones I showed you. There will be spectra, both with TV and conventional cameras. There will be conventional cameras. There is a LiDAR, which is what this is supposed to represent. It's look for dust behind the meteors. This is representation will be a ground-based radar that Peter Brown and Jim Jones and others at Western will be running at the same site in conjunction. By the way, the plan is to fly these south of Thailand. It's the current plan at the date of the 1998, at the time of the 98 maximum. Those are what is planned in the way of experiments. As I mentioned, we're involved in the image intensified video part. As I say, other Canadians are involved in the radar part. These are the things that we hope to. This will be, I think, the largest coordinated campaign of meteor researchers using different techniques probably ever done. We obviously want flux, mass distributions, light curves that tell stuff about physical structure. We want to look at chemical composition through the spectra at the heights that these meteors occur. There's a paper about to come out from some Japanese people that have found a meteor at 160 kilometers, so 2 Leonid meteors actually at 160 kilometers. Look at the orbits, it'll tell us about how they're ejected from the comet. Weight is the degree to which the meteor's light is coming from more than a single point. We'll look at that, look at the chemistry of the persistent trains. Why an airborne observation? And by the way, well, let me do this first. It allows you to avoid bad weather because the region in Asia where it is, there's nowhere you get much better than 55 or 60% chance of that time of year of it being clear. So we'll be above the clouds. We'll avoid some low altitude dust. Probably the most important thing is it'll enable us to move a little bit beyond what you're limited to on ground in terms of the wavelengths that are accessible. And then just the fact that you're bringing scientists together for this observational period and a lot of collaboration. Why 2 airplanes? Because that doubles the cost pretty well. Really, you want to have most physical processes depend on what the height is. Your data is so much more valuable if you have triangulation and know those heights. Is from my point of view, the dominant reason to do it. I think I will just very quickly show the last couple of slides. You okay, Richard? This is a picture of a micrometeorite that Don Brownlee and others have done a lot of work in studying. The scale on, I believe this one is about 1/6 the width of a human hair from one side to the next, so it's a very fine scale. You can see even on this, there's lots of evidence of a very kind of fluffy, fragile grain structure, which some of us believe apply to the Leonids, so it's by no means proven. I wanted to point out that there is zero danger that this is going to happen during the Leonids. There's a picture of Arizona meteor crater. Just to give you some sense of how steep those cliffs are. I was at a conference, we had an expedition led by Eugene Shoemaker, late Eugene Shoemaker, down to the bottom. So there is no chance of big objects impacting, nor is there even chances of objects this big impacting, like the Peekskill meteorite that some of you know about going through cars. It's estimated that the parent comet can at most eject something of a few kilograms size, and it's probably cometary material, so will not reach the ground as meteorites. So no matter how strong, we don't expect meteorites on the ground from the Leonids. I'd be happy to be proven wrong, but that's conventional wisdom. This is mainly why I went to the slides. This shows some of the work we've done at Mount Allison looking for wake in these faint meteors. This is a false color image of a little region around a meteor. Now the ones you saw in there look to have big tails behind them, as though all the stuff was screwed out behind them. That's almost entirely an effect of simply the observing equipment. So we've gone to ways here where we have short effective exposures of just a millisecond or a microsecond or so. If you had no wake, you would expect that the image of the meteor, which is the yellow thing there, would appear nice and circular. And we would argue within error, or within measurement uncertainty, that one is circular, so there's no real evidence of wake. We did detect a few like this that do seem to have evidence of wake. Surprisingly few, and that's somewhat inconsistent with this picture of crumbly grains. So kind of the main two things that we're working on in our research program, looking at light curves where we seem to need them crumbly, looking at wake where we seem to need them uncrumbly, are somewhat at odds, and we hope to straighten this out. I have some hopes of getting more sophisticated equipment that will allow us to do much shorter effective exposures with much better precision, which should answer this. That's the last slide. Well, the very last thing that I said I would do in the talk was speculate on why the Leonid storm. Why is it, I mean, you get outbursts from the Perseids. When the parent comet broke up, the Andromedids produced pretty strong showers. The Draconids, yeah, they get to storms. In fact, 1998, we may have a Draconid storm in October. It's a great year for meteor storms. But in general, meteor showers like the Orionids and so on never storm, even though the comet's much bigger. Why is that? Well, a simple answer is for a brief story. Yes, time for one brief story. I got to tell you this story. The story I like, Scott, in a way nothing to do with Leonid meteors, but the answer to the question. When this was now a number of years ago, when my daughter Erin was about 5. We were driving into Sackville, and there's this big full moon up in the sky, and so she was in the back seat with her little sister Laura, and she said, "Daddy, what holds the Earth up? Why doesn't the Earth fall?" And if you're a physicist's father, this is the sort of question you wait for from the time of conception. So you go through this elaborate explanation about how there's no force pulling it down. So by Newton's laws, but you don't use Newton's laws for a 5-year-old, that it doesn't need anything to hold it up, and so on. And so there was a little pause from the back seat. We were almost in the cycle, and she said, "Daddy, what holds the Earth up?" So I was crushed, but I went together and put an even better explanation of Newton's second law, and it seemed brilliant. There was a long pause. We were almost into Sackville, and then this little voice spoke up for the third time, and she said, "Daddy, you don't really know, do you?" And the simple answer is, I don't think anyone knows the answer to this question, and I don't actually know of anyone that's even taken the courage to speculate in writing in a very detailed way the answer to this. So someone that's looking for a good project out there, this is the one. Well, all right, here are some possibilities. The parent comet's small. I mean, for example, the Eta Aquariid and Orion meteors that come from Comet Halley, the Perseids from Comet Swift-Tuttle, there's no doubt that those parent comets are much bigger, are like 15, 18 kilometers. This is 2 kilometers. We would expect that the gas flow is much less from this comet. They're ejected with a small relative velocity. That tends to keep them all together. Maybe that's why they storm. I don't think that's enough of an explanation by itself. What else is special about the Leonids? Well, they have 71 kilometers per second, meaning that they are almost the limit of being a parabola as opposed to an ellipse. So maybe it just takes a little bit of radiation push to make the orbit big enough that it gets hopelessly lost as a Leonid, and that keeps cleaning out all the old stuff, and so all you ever get is this fresh stuff that you have in the storm. Or maybe it has something to do with the fact that Jupiter's period of 11.86 years is roughly 1 to 3 ratio with the period of this comet, and Jupiter, what a resonance effect, periodically cleans out the Leonids and you get storms. I don't believe the fourth one at all, but someone at least had the courage of proposing it at a conference I was at, and that maybe there's a 5 to 2 resonance with Uranus. Or maybe it's just that this comet, maybe it's related to the fact, why did no one see it the year it was 0.008 AU? Maybe this comet simply is very dirt covered, maybe it has a very low gas to dust ratio, all of those things, so that it produces mainly meteoroids, but at very low relative velocities, keeping them all in a nice little packet. Or maybe there's some reason that no one's thought of yet. I think we truly don't know that. I thought I would just end with the other famous picture from the 66 Leonids that you see all over, and I'd be pleased to try to answer any questions that anyone would have. Yes?
Can you explain again why the radar is more speculative than the sun?
Pardon me?
Why
Oh,
the radar
why? Yeah, let me put the overhead back. It's,
intuitively I would get speculative reflections.
that it's not that it's more specular from the side, it's just for the particular time that I've drawn, with the Leonids going like this, the only ones that meet the specular condition, that is, that are perpendicular, is this one. Right? Like, I mean, if you looked at a later time, like early in the night, the Leonids are going about like that, it'll be the beam up here that will be the specular one.
It's that thing when you say perpendicular, particle itself, it's the surfaces of the particle that when the perpendicular to get speculative reflection, not the velocity.
What you have when the meteor comes into the atmosphere, it creates an ionization column. So it's a column of electrons, an electron density cloud. To some degree, it depends a little bit whether they're what's called underdense or overdense, but to some degree we can imagine those each as kind of scattering stuff back. But many of those will interfere with each other. The ones which don't interfere are the ones near the perpendicular. So it's not like a glowing cylinder, although to some degree an overdense one is. but it's just that if you kind of work out the kind of the interference effect, it's the ones that are all near that perpendicular that are the main ones contributing to what you see. Is that okay?
Yeah.
Yes, David?
What is the wavelength of the radar use?
Well, it's what? 3 by 10 to the 8th divided by, well, oh, 3 will be nice. I like doing numbers like that in my head. By, if we use the 30 megahertz, remember we're going to use 2 frequencies, that will be 3 by 10 to the 7th, so it's about 10 meters. The other one's 15 meters, I guess it works out. Yes?
Which raises another question. Why the 2 frequencies? What does that give you?
Now, you should have the non-existent radar people here to answer that question, since I never use radar, and there's probably people in the room here that know more than I do about it. I believe the arguments are related to the fact that in some ways, this interference effect is a real problem in that you have what's called a height ceiling effect, and that the train begins to expand. Okay, like in the atmosphere, you've created a column of ionization, but really rapidly that ionization gets bigger and bigger. And when it gets comparable to the wavelength of the radar, then you get no echo. And for that reason, the Leonids are just terrible to observe in general by radar, because the meteors, past meteors occur higher, therefore the trail expands faster, and that argues against detecting it. Now you might say, the way to get around that is I want to choose a radar that has some huge wavelength, because it'll take the trail a huge time to get there. Now, all of that I'm sure of what I'm telling you. The next part I'm not so sure, but I believe, though, there is a contrary kind of argument to that, in that you will get absorption if you go too far in that direction, so that limits you. I'm not absolutely, like, the 20 and 30 were actually set by the fact, remember, that we're basically renting a radar that was built for something else. I believe those are the limits within which it can be frequency agile. And so that's as far as they can go in trying the 2 extremes, is, I believe, the simple answer. But that may not be right. Ian?
Question about the hazard to spacecraft. A year ago, Tony McDonnell was here in Ottawa briefly, and he's at the University of Kent in Canterbury, England. He was in charge of the dust experiment and the Giotto mission to Comet Halley. And I asked him in regard to the Leonids what he would do for a communication satellite if the shower was performing. He said he'd turn it off for a couple of hours. Is there any plan to do that?
I don't know. I suspect, one thing I didn't describe here was what the various organizations that are funding this kind of want us to do. And what they want is, by next May or June, a report on what the prediction is for 98. And I think based on, losing a couple hours of communications time is also with that. If we tell them that the hazard is going to be great, which people at Western are going to model from our data, then I suspect someone will choose to do that. The people that are funding this particular program are not actually people that run any communication satellites. To my knowledge, people in our group have not talked to them. It's mainly NASA, whose main concern is actually with things like International Space Station, as I understand it, and to some degree Hubble and shuttle missions and other things, and military, where I'm not sure what exactly they will do with our data, but they're partly funding it, both Canadian and U.S. military. Yes?
In a geostationary orbit, you can't really use the Earth much as a shield.
Correct. That's right.
There's
There's a restriction in those. I might also, I don't think I mentioned here, what seems like at first the right thing to do with the solar panels when you have the choice, that is, radiance coming here, you put them flat on. Some people argue may not be the right thing, because although you greatly lessen the chance of an impact, you do mean that a few of them are going to be skimming almost along, and electrostatic discharge may be more dangerous. Some people that know more than I say of that, so that's not as obvious as it might be. The other possibility that in their paper, Martin Beach and Jim Jones speculate, and Peter Brown on, is kind of deploying some kind of a shield in the direction of the Leonid radiant to kind of an extra shield. And I don't know whether there are some missions that is at all thinkable even doing.
How effective will camcorders be on the actual night of the shower?
I think I actually have an overhead that gives that answer because I was presenting a paper and someone made up the wrong title for me. So the title was use of, something in camcorders. I never had any plan to talk about, but I put in the title, and so I never got around to changing it. So I said, oh, that's interesting. I should actually calculate that. So I calculated a typical camcorder, if you put it on zoom setting, will, at least with my camcorder, we'll see, barely 2 magnitude stars. I don't know if you've tried yours or others. That new ones may be a little better than that. That's about the limit. If you put them on wide field, they'll see less than that, kind of around 0, something like that. Then I worked out for both of those kind of how many meteors you'd expect. You have to assume what the mass distribution of sizes are, and that's not too well known for the Leonids. But with those, you still were looking at the fact that you might be getting a few per hour during a pretty good storm, like a few thousand a meteor an hour storm, but it won't be more than that. Nevertheless, it might be worthwhile doing that because all these image intensified ones are monochrome by their nature, and so you'd have color, which would be nice. I also did a calculation of using like the electronic shutter, which would be nice to do my wake stuff, but it gets really depressing actually. You've got so little light then. Your odds of getting one, it's something a little less than 1 over a few hours observing. But nevertheless, I hope someone in the world tries doing all these things, because even if each camcorder only gets 2 or 3, if 400 people did it, we'd have a lot of color images of Leonids, which would be potentially valuable. I think there are several independent but non-competing groups trying to coordinate sort of things like this and visual observing and so on. Peter Brown has his international Leonid watch. Peter Janiskin's kind of is doing a somewhat separate one. There was a message came out about another one through the North American Meteor Network. So I think you'll see a lot of kind of plans to do this. Yes, Dan?
Can you give us another magnitude for the diameter of the ionized trail?
In general for meteors, okay, this isn't really a Leonid-specific answer, but most people would think the Leonids won't be different, probably. In general for meteors, it's the order of a meter or so originally, what's called the initial radius. But at high height, it really rapidly, a fraction of a second, expands, into your tens of meters, or at least 8, 10. Yes?
When you're talking about showing the satellite off,
Yes.
the electrostatic discharge, where is that electrostatic energy coming from? Most of these satellites are not going to be ionized in the atmosphere yet. The impacts are mostly physical.
Yes, I believe so. You're stretching my knowledge, which I'm more or less reporting on others here, but nevertheless, you have like a hypervelocity impact. It's got loads enough energy to kind of immediately vaporize, and it's got enough energy to ionize those. So it's the actual impact. It's not the ionization that you get from lowering the atmosphere. Yes?
I would like to take the chance to add my comment on that. I thought the satellite different surface have various potential, and with these clouds of produced by the impact, then you can have discharge between, like a strike between the cloud, for example, then you have a strike between different parts of the spacecraft.
Yeah, the plasma that's created by the hypervelocity only provides an ionization path. It's the pre-existing charge differentials. And Ian's exactly right. I think if your electronics wasn't running, I don't think that that's a hazard. So that would be a simple mitigation. On the other hand, you imagine turning off all the communication satellites in the world. If everyone did this, we need some satellites running. But I suspect part of the reason people want estimates is just so they can kind of be prepared. I mean, is there likely going to be one satellite go down in this or none? I think we know the answer to that. I think it's somewhere between none and one would be my prediction. Not this year. I would place a lot of money, none will go down this year, but in 98.
Will impacts be be too small to be registered on the moon? If they miss the Earth, they hit the moon?
That's a really good question, and I haven't thought about or looked at that. I don't know if there's anyone in the room that knows. I would think that, do you mean by impacts, actually seeing a cloud of dust stirred up by someone that's looking through a telescope at the moon at the time?
Right, or any existing instruments that are still functioning on the moon?
Yeah, I asked someone, and I was surprised by this, but I asked someone, were there still any working seismographs radiating stuff back to Earth? And they said no, if they were right. This was at a meeting we had at NASA in Houston in May where we looked at different ways of getting data.
Mm-hmm.
So if the person that told me that informally was right, the answer to that part's no. I would think, given that the biggest one we think is only about 2 kilograms or something, we think the biggest one ejected from this comet's about this, that even with a powerful telescope, you're not going to have seen, I think the probability, I don't know. I don't think you'll see it on the moon, but I haven't worked out the probability of that. Is there a question here somewhere? David?
Yeah, I think there's two other points that one of your programs will be looking at chemistry. I just wanted to explain the core quality of the spectrum you represent, or what you would be looking for in chemistry.
These poor quality spectra here are not part of the official program. We're going to do them because we kind of have one camera that's totally ours that we do what we want with. Our goal there is more to designing an optimum observing system for 98, and that they'll tell us which regions of the spectrum. So if we wanted to do, you know, kind of something, because it's ultimately the sky background that limits you. It is true that in the 98 campaign, I listed chemistry as one of the goals. That is not mainly with the TV spectra. Remember, there are conventional spectra, and there's even very high resolution spectra. Some of the other experimenters not on. But there is a plan to do some of these low resolution with Yuri Borodika, who's one of the PIs from Czechoslovakia. He's better than us. He's kind of learning about spectra. I think a lot of good advice. Let us know. These were the first spectra we've actually ever done once this summer.
Well, perhaps if there are no other questions, we could sort of break up, and if anyone wants to ask Bob questions informally afterwards. And it has gone 9:30. It's getting late. Do you want to break the formal proceedings now? You did say you had some peak skill there for people who haven't seen it, a little extra sort of peak skill media, right? But,
these are the most impressive meteor you'll ever see, those of you who have it. I think we should be right there.
And this did drop Sunday.
Yeah, this is what produced the hole in the car that I showed, and
12 kilograms.
Several of us worked out the orbit and the atmospheric fragmentation. It had the good fortune to occur on a Friday night, in October, when lots of football games were on. So that's the fireball coming in and breaking up. Altogether, we're able to secure 16 different amateur videos of this event, partly because it came in even flatter than it seems from here because of the perspective effect. And we estimate it actually glowed for about 42 seconds. It was about 23 tons before it came in. October 9th, 1992. And some of you are saying, wasn't that El Paso thing on the same date? Yes, it was. Also, the Draconids are on that date, but this has nothing to do with the Draconids, contrary to some media reports. This is one of the nicest ones. It's a shot looking over Three Rivers Stadium in Pittsburgh, where a National League baseball game was on. Is that?
Stadium seems to be a nice place to watch for.
That's right. And Someone commented after our paper was in Nature, David Hughes wrote that maybe we should all park old Chevys as bait for meteors. I have a 9-year-old Chev, but it hasn't yet been hit by a meteor. To some degree, it's appropriate showing this, because even though it has nothing to do with the Leonids, we're going to see the meteor here in a moment. Going on the right, his friend will say incoming when we have the audio, and there it is. In that, to some degree, the work on the danger of the Leonids and the Perseus to spacecraft was born when Peter Brown and Martin Beach, then both grad students from Western Ontario, were driving down to the US and chasing up these videos. And they had the idea that it might be important, and that subsequently published in some papers, and advice has been taken to heart by several things. NASA delayed shuttle missions, reoriented Hubble, and closed the cloud, for example, based on their predictions for the Perseus. It's a very nice picture. But let me tell you, trying to get scientific data out of handheld, uncertain where you are, uncertain what the coordinates are, with no celestial references, is a fun game. This is the only one that we were able to get a celestial reference. You see the full moon in this one. It's also a bit better quality. This was actually shot by a professional sportscaster. We knew exactly where we were, and we got a plan of the stadium, plus we had the moon, so this one we had pretty firm. That's the full moon just above the meteor. You'll see a couple flares. We had one already. There's one. I didn't bring any still pictures with me. We have a couple still pictures that are just spectacular. 1/400th of a second pictures. One of them shows 90 individual fragments from this. This is very boring, especially those things. Okay, I'd be happy to answer any questions people have. I thank you for your attention over a long time. Yes, David.
Ask one more. What increase the chance of getting of a meteorite surviving the entry in the atmosphere? Is it steep angle or shallow angle?
The answer to that, I believe, am I right here? Would you expect a steep one to be more fatal?
Yes, I think so. It gets over the trouble quicker and doesn't stick there as well.
That's right. So, I mean, this one survived kind of not because it was almost grazing. Because it was almost grazing, we got loads of pictures. But that actually is why it ended up in the biggest pieces like this, I guess. I've not actually seen it. You have a model, right?
Yeah, we've got a class model, but like this, so it's 12 kilos.
Yeah. But remember, we estimated it started at 23 tons, which is still not a big object. It's kind of like this.
But it hasn't, I was pointing out earlier, that the peak scale has a very thick fusion crust in comparison to other meteorites that I've seen. Most stony meteorites have very thin fusion crust. Peak scale's at a couple of millimeters. It's quite noticeably thick, which to my mind suggests that it's consistent with this very relatively long shell.
Covered a lot of ground.
That and the paint on the car.
Pardon me?
That and the paint on the car.
That and the paint on the car, yes. National Meteorite Collection that Richard handles, they have a piece that's got red paint on it from the car. I have an old red shell. I was hoping it's being hit because, in case somebody didn't hear, Michelle Knapp, who was the person whose car it hit, she was 18 years old. She bought the car for $100 from her grandmother. It was parked obviously in the driveway, and there was this big bang, and they went out and found there was actually a little crater underneath. And she sold the meteorite a couple weeks later for $59,000. The craziness of meteorite prices in the U.S. And she auctioned off her car at a mineral show later for another $10,000. And then the collectors who bought it cut it into pieces and made a tidy profit and resold
Not
it.
the car, meteor.
No, that's right. The most interesting part of this story, which Peter Brown claims to me is true, is the police officer that was called to investigate this wrote down in his report that this hole through the car, you saw it in the slide, was apparently created by a jealous male.
No, burly male.
Pardon me? A burly jealous male, right.
Right.
A very burly male. Anyway, well, I hope your cars have been hit with meteorites while you're here, and Richard will buy them from you,
No.
right? But not for $59,000.
They won't be worth the car, maybe, but since meteorites are priced per gram, I'm really, really pleased to hear that even if a Leonid survives, there won't be very much of it.
Wow, I would bet that no Leonids will survive.